the mathematics of Coulomb's law. Let's first define coulombs. The force of attraction or repulsion acting along a straight line between two charges is directly proportional to the product of the charges and inversely to the square of the distances between them. In other words, Coulomb's force, which a lot of the times I will abbreviate this as the electric force between two charges, has a constant of, there's a proportionality constant times the magnitude of the two charges divided by the separation between those two charges, and r hat 1, 2 is the direction. Where I should, let me box this. I'm going to move this over a bit, where we have two quantities. We have the displacement vector has magnitude and direction. And so we then say that the magnitude is the length of that vector. And the vast majority of the time, when we talk about the direction of the displacement vector, we define it as the angle theta 1, 2. And then we have our proportionality constant, which is 4 pi epsilon naught. And many times people abbreviate that with K, and this value is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. So if I look at the units, of course, the units of force are newtons, charge is coulombs, the displacement is in meters. The only units that we care about right now is the units of this epsilon naught. So if I look at these units, it turns out to be coulombs squared Newton meter squared. So in simple terms, or in simpler terms, Coulomb's law states the closer the charges are, the stronger the force between them. Now note, we already discussed this in detail in our very first lecture. Now, let's look at some things that I should mention here. So here's, how do I say this? Here's some remarks about Coulomb's law. The first thing that we should talk about is that the absolute electric permittivity, excuse me, is defined as epsilon, not epsilon naught, epsilon. So the absolute permittivity is a measure of how easily the electric field lines can pass through a given material. In vacuum or dry air, this is called the permittivity of the vacuum with value of epsilon naught equal to 8.85 times 10 to the minus 12. Now the units, there's an F here, and that F stands for farad, which is a unit of capacitance. But for right now, we don't really care. So this is a value that sometimes is very useful. Most of the time, I would actually use 1 over 4 pi epsilon because that's an easier number to remember for me. Okay, that's the first remark I want to make. Now, we should talk about two other remarks, which I think are really, really interesting. So the first thing here is that we should talk about the range of validity of Coulomb's law depends on two situations or factors. So the first one that I should mention here is that if the light quantum particle and that's what we call the photon, has zero mass, then Coulomb's law is valid as R goes to infinity. However, all electric forces at as R goes to infinity are zero anyways. In other words, it has infinite range. That is, it has infinite range as long as the photon has zero mass. Now, there's another one that's typically not mentioned from quantum field theory. If let me be careful, if a charge gets really close to another electric charge, let's say of the order of 10 to the minus 20 meters, negative 12 meters that is, then a quantum process occurs called vacuum polarization. That makes Coulomb's law invalid. Now, here's the last thing that I want to say is that 3. When calculating Coulomb's force, the most important property, or excuse me, not property, the most important quantity is the displacement vector. In fact, this is such a big deal that I'm going to change its color. So the displacement vector is the most important thing. And what you're going to see here is this, as I'll show here in a minute, that because this force works on straight lines, what you're going to see here is that when I look at the magnitude of the force, this is proportional to 1 over the displacement vector squared. And the direction of this force will be in the direction of the displacement vector, which the majority of the time we call it the angle, theta 1, 2. So let's look at some problem-solving strategies. And as always, these are only suggestions. And you should operate, you're going to have to make this your own. Different textbooks are going to do different things. So this is sort of like the outline that I typically do. So step 1, use consistent units. You got to be careful with the units. It's really easy to mess up the units because they're quite large. So if I'm going to use the K value of 1 over 4 pi epsilon naught, distances must be in meters, charge in coulombs, and force in newtons. So everything has to be converted into those units. When forces acting on a charge are caused by 2 or more other charges, the total force on the charge is the vector sum of the individual forces. In other words, superposition is what dictates what the net force is going to be. Just like in physics, 4A or your calculus-based mechanics course. The force, you must always set up a coordinate system. Now, we haven't talked about the right-hand rule, but you should think about using the right-hand rule to set up a proper coordinate system. Because when we get to magnetism, we do the exact same thing. 3, the electric force between 2 charges is the vector force, which we already written. And so this force acts along a straight line. That means from the center of mass of one charge to the next. The direction we already talked about is R12. The key factor in determining the electric force, or the E force, again, is a displacement vector. A lot of the times we do calculate the angle using the tangent inverse, but you're going to see that sometimes we'll have to use either the sine or the cosine as well. And then we calculate the vector with the magnitude of the vector. Something that's missing here is that I didn't put the absolute value symbols on the charges, and the direction of the electric force is always in the direction of the line connecting the 2 charges.